Hello and welcome to a new episode of Differentiating by First Principles, Sine X and Cos X. Now, if you haven't not seen the first Calculus 1 video on differentiating by first principles via polynomials, I would highly recommend seeing that video first and then going to see this. This is in kind of the start of A-level maths rather than AS maths. However, this is used more in exams and whatnot. So I'm going to show you how you can differentiate both sine x and cos x, and then therefore you'll be able to use that knowledge to differentiate minus sine x and minus cos x. Okay, so let's get started straight away. As you know, the gradient, or dy by dx, is defined as y2 minus y1 over x2 minus x1. These are your individual coordinates, and then obviously this is equal to dy by dx. And that's what we're going to be using. This is the same, this is almost exactly the same as in the first video that I did with polynomials. Now, we have to determine what is x1, x2, y1, y2. Okay, first off, we are going to prove that the derivative of sine x is equal to cos x. How are we going to do that? Okay, let's begin by saying, let's begin by saying that our x1 coordinate is our function, okay? Our x1 coordinate is always x, always. And our x2 coordinate is always x plus h, okay? This is true for all gradients with x1 and x2. Our y1 is our function, sine x, and our y2 is going to be sine bracket x plus h. That's what we're working with at the moment. Now, if we put everything together and then determine the gradient, we are going to say that the limit as h tends to 0, just like in the last episode that we did, of sine x plus h minus sine x, all divided by x plus h minus x. That's what we are working with at the moment. Okay, so how are we going to determine this? I shall show you. So if you recall that sine x plus h is equal to sine x cos h, not to be confused with cosh, plus, sine x plus h plus or minus cos x sine h, not to be confused with sine, our hyperbolic function. So, by using this, we are going to substitute that within. So, if we say that the limit of h tends to 0 of sine x cos h plus cos x sine h minus sine x is all divided by h, because x minus x is nothing. Nothing we can do about that. So now what we are going to do is that we are going to factor sine x and cos x individually. So what we are going to get is that the limit as h tends to 0, all in big brackets. So what we are going to get is, so if we factor sine x, we will get that cos h minus 1 all over h sine x. That's what we're going to get. if we factor cos x, we will get nothing. We will get sine h over h, because there's no other factors within sine x over cos x. Okay? So now, we are going to recall small angle approximations. So, sine theta is approximate also to tan theta, which is also approximate to theta. So therefore, sine theta and tan theta are approximate to theta. If you don't know why, let me show you. So, if you have a graph of sine x, just say it's... Okay, let's say if we have a graph of sine x and then a graph of tan x. Just something like that. When we consider small angle approximations, so when we say when theta is small, so when theta is small, so y equals sine x, y equals tan x. What we get, if we zoom in right by the origin, what we will get is as a straight line when we zoom in right to here. So what we get is that y is just equal to theta, where the gradient is just 1. Exactly the same with tan, well, sorry, that's meant to be theta. And then that's why these approximations are the same. With cos, it's a little bit different, because obviously we have a curve to consider right here. And if we zoom in on that curve, what we will get is that cos theta is approximate to 1 minus theta squared over 2, where obviously 1 is the y, cuts the y-axis, and theta squared over 2 is just our equation. So what happens is, if we only consider, so if we consider cos h minus 1 over h, if we approximate this, what we will get is that 1 minus h squared over 2 minus 1 over h. So what we will get from that is h over 2. And so as h tends to 0, cos h minus 1 over h is equal to 0. Okay? So therefore, this sine x term will go to 0. So this time, if we consider sine h over h, what we will get is h over h is equal to 1. So as h tends to 0, sine h over h is equal to 1. Therefore, what we can say is that, I hope you can see this, so therefore, as limit of h tends to 0, 0 sine x plus 1 cos x. So therefore, root f of x is equal to cos x. I'm sorry this is like really messy, but it's necessary. So therefore, we have proved that the derivative of sine x is cos x. And this is the exact proof that you use. I believe there is another method to it, but I'm not sure what it is, and frankly, I cannot be bothered to do so. So, now we have differentiated, we have determined that that the derivative of sine x is cos x. And I hope that has helped so far. So now what we're going to do, we're going to do the other way around. We're going to prove, so prove that f of x equals minus sine x from f of x equals cos x. We're going to prove that way, okay? So we're going to do exactly the same again. Our x1 is just x. Our x2 is x plus h. Our y1 is cos x, and our y2 is cos x plus h. So it's inside the function. That's what we're going to do at the moment. So our gradient is the derivative. So we're going to say that the f dash of x, x prime of x, is equal to, so the limit as h tends to 0, so y2 minus y1, so we have cos x plus h minus cos x all over x plus h minus x, okay? So we have to recall, so recall that cos x plus h is equal to cos x times cos h minus sine x sine h. So it's different this time. So plus or minus is equal to minus plus, okay? So we're going to use this, we're going to substitute it back in like we did with sine x. So we're going to say that the limit of h tends to 0 is equal to cos x cos h minus sine x sine h minus cos x all over h, okay? So now what we're going to do, we're going to factorize as normal our cos x's and our sine x's. So we're going to say that the limit of h tends to 0, this statement always stays the same throughout all the way. So factoring cos x, we will get that cos h minus 1 all over h sine x minus, cos x minus sine h over h is equal to sine x. Okay? So now, using small angle approximations, by working it all out, at the moment, we can assume that cos h over h tends to 0 and sine h over h tends to 1, okay? Sometimes, if you're lucky, if you're not good with small angle approximations, you'll be given these assumptions where cos h minus 1 over h tends to 0 and sine h over h tends to 1. But in the most cases, and it's better, much better, if you use small angle approximations to work to determine if it tends to 0 or, as h tends to 0, okay? So, what have we got here? So, we can say that f of x is equal to the limit at h tends to 0. So this tends to 0, so we substitute in 0. Cos x minus 1 sine x. Therefore, the derivative of cos x is equal to minus sine x. And then obviously, for example, if you're given a coordinate let's say that work out the gradient. So what is the gradient at the point, I don't know, say 12, 4, for example, at those coordinates. So what would happen is you would work all of this out, and then you would substitute in your 12 x coordinate into this value, and then you will get, I don't know, a random value for it. 12 is a bit over the top, but I hope you understand where I'm going with this. So that concludes with the episode. I hope you'll be able to work out, actually, give you the questions. If you can do these by heart without guidance, you have already nailed it. So these are the 2 questions that I hope you can do. So next time we'll be doing more differentiation on this chapter, and then that's pretty much it. Thank you very much for. Also to mention that you can also get something within tan, cosec, cot. You can get a lot of things. However, what you can do, instead of using first principles to work out what tan is, we use the quotient rule, and that is what I'll be discussing in the next episode. So, in the meantime, do these questions. Thank you very much for watching. Hope you have a good day, and thank you very much. Cheers.